All right, let's go and get started. As I was saying earlier, I have a little bit of a cold right now, so if my voice is a little off, just bear with me. Let me go ahead and get the sign-in sheet passed around. So just a little bit on housekeeping. Everybody should have all of the handouts and whatnot for the next little while. I'm going to go ahead and give you all a homework today on geometric properties of area, things like moments of inertia and whatnot that we discussed last time. And then shear and moment diagrams, which is what we're going to be discussing now. Let's see, 1, 2, 3, 4, 5, 6. There you go. And there you go. All right, we'll probably get through the bulk of shear and moment diagrams today. If not, it might bleed over a little bit into next time. But I'm going to have this assignment due a week from today. The first problem, my advice to you is to use Excel or something like that because it's very repetitive in terms of the calcs. And Excel works really nicely. If you want, do it by hand, that's fine. If I remember correctly, that problem is in metric and all of the dimensions are in millimeters. So when you do the math, you're going to get, some really large numbers, like for moments of inertia. I mean, we're talking like 10 to the 9th or something like that. So don't let that scare you or freak you out. It's because we're talking about, millimeters, where a millimeter is very small. To define the shape, it might be 400 millimeters, and then you're taking a number like 400 and raising it to the 4th power. So they get large really quickly. So don't let that freak you out. All right. So let's get back to sort of our general topics of discussion. And really our focus right now is beams. The whole concept behind moments of inertia and what we're talking about now, shear and moment diagrams, is to be able to assess bending stress. Now, in order to assess bending stress, we have to cover 2 preliminary topics, hence geometric properties of areas and this. Now, I got to apologize to my structural analysis folks in the room because they're going to get bored probably real quick, but they'll be all right. They'll make it through this, and hopefully you will too. If I had to guess, you have at least seen the concept of a shear and moment diagram in some of your courses. I don't know how deep you've gone in, let's say, statics, but regardless of if you spent hours upon hours on them or you've never seen them, I think this will be pretty straightforward. Our shear and moment diagrams in here are going to be fairly basic. The more advanced stuff is for a course like structural analysis. All right. So instead of going through the whole, I'd say, kit and caboodle with shear and moment diagrams, because there's a whole host of different ways of looking at it. You could draw shear and moment diagrams using a tabular approach. You could try and derive an equation. What I'm going to do is use a graphical approach. And in order to understand that graphical approach, I need to do a little bit of a derivation. My derivation is going to be on a beam subjected to some arbitrary load, just some load W. It could be any magnitude, anywhere. It doesn't really matter. It's just some load. I've got it drawn positively, so it's going upwards. Most of our loads will be going negative. They'll be going down, but that's okay. I cut myself out a little slice out of that beam, a little differential element that's dx wide. And I say, well, the load probably varies across the beam, but across that little differential element, remember, we're talking about a differential. It's really, 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 really thin, okay? Along that differential element, I'm assuming that the load is constant. Now, I've got shears and moments on either side of that cut, and I've got them drawn in their positive directions. Remember, that's our sign convention. But keep in mind, from one end of the segment to the other, there's a change. If I've got some shear force here, I've got a shear force here plus, some change in shear, some dV. Same thing with moment. If I've got a moment on the left end of the cut, I've got a moment on the right end plus some change, some dm, right? The idea is that from one end of the segment to the other, I get a little bit of change in shear, a little bit of change in moment. Sound good? I then use equations of equilibrium to say, all right, can we determine those? And you're going to find it's pretty basic, okay? So we're going to use equilibrium to determine how much that dV and dm changes from one end of the element to the other. So just treat it like you would any statics problem. So we sum forces in the y direction, so everything going up has got to equal everything going down. So what do I have? I've got V going up, I've got V plus dV going down, and then for my load, I've got it going upwards, and it's not W, it's W acting over the length, acting over dx, so W times dx. Sound good? It's like if you have a load of 2 kips per foot over 30 feet, the load's not 2, it's 60. All right? Make sense? 60 kips. So your dV's cancel, or your V's cancel, sorry, and you get dV is W dx. All right? Same thing with the moments. We can do something very similar. If I sum moments, let's say on the right side, I've got an M acting this way and an M plus dm acting in the opposite direction. This shear does not cause any moment, but this one does. V times dx acting clockwise, and then I also have my distributed load acting clockwise, and it's a force times a distance. The force is W dx, W over that length, and the moment arm is half a dx. Remember, it's in that range, in that differential element, we're considering it uniformly distributed. So the centroid is halfway over. Sound good? Now, when you carry all that out, you get a dx squared term. And keep in mind, we're talking about a dx, a differential element that's really, 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 really thin. And we're taking that number and squaring it. What happens if you take a really small number and square it? You get a really, really, really small number. So I propose that this W dx squared over 2 is negligible. We don't have to worry about it. So we can just say that that goes to 0. And we get the following relationship that dm is V dx. Do a little bit of division, and this is basically a pretty straightforward calculus type relation. The idea that if I want to determine the shear, I can just integrate the load diagram. If I want to determine the moment, I can just integrate the shear diagram. So it gives us some pretty straightforward relationships, okay? And you'll hear me use some language, things like lot to a little and whatnot when we draw moment diagrams that I think will explain this pretty reasonably. So if we're looking at the relationship between load and shear, we can say that at any given point, the slope of the shear diagram is equal to the load because dV dx, that's the slope of the shear diagram. It's the derivative, right? And between 2 points, however much change in shear is that we've got is equal to the magnitude of the load between those 2 points. In other words, we're just integrating, okay? Same thing's true on moment. At any given point, the slope of the moment diagram is equal to the value of shear. And between 2 points, just integrate the shear diagram. Pretty straightforward. The nice thing about what it is that we're doing is when I say integrate, you're going to see here in a little bit, I mean, let's go back to Calc 1. What does it mean to integrate a curve from A to B? It means to find the area under that curve. Well, if your shear diagram is a bunch of rectangles and triangles, do you really need to break out the calculus? No. I mean, you can calculate the area of a rectangle, just B times H. You can calculate the area of a triangle pretty straightforwardly. So we can draw shear and moment diagrams graphically. We don't really need the calculus in most cases. So we'll see how that works later on. Okay. We do need to have at least a brief discussion on support conditions. Support conditions are what affix the structure either to its next adjacent component or to the ground, okay? And the main purpose of support conditions, other than transferring the load to the ground, is to keep the structure in equilibrium. So we need to talk about the different types of support conditions that are available in the world of engineering, and really we have 3 of them, okay? Now the first one we term a pin support. Pin supports are designed to resist motion in, let's say, the X and Y direction, if you want to use X and Y, to think about it like that. But the thing about pin supports is they allow rotation. You think about this door, okay? I can take this door and I can sort of push on it like this, and I can pull like that, but it freely allows rotation. Make sense? All right. So that's a pin support. A roller support does the same thing as a pin, but it allows that translation. It allows lateral translation. You see stuff like this a lot in, let's say, bridge systems. You might not see a literal, cylindrical wheel on the bridge, but you might see something like the difference between a fixed bearing and an expansion bearing. So the idea behind that is, and this actually relates to something we've talked about earlier, let's take a bridge in, let's say, West Virginia. Our summers can get to, like 9,500 degrees fairly easily, and our winters can go below zero, right? So what's going to happen to that bridge throughout its life? It's going to expand and contract, right? So we create one of the supports, or we affix one of the supports using an expansion bearing, which is basically saying we affix the girder to a sole plate, but we use slotted holes to allow it to translate a little bit. So the idea is that it's still being held up and down. It's not going to fall, but it's allowed to move a little bit. Does that make sense? So we do that pretty quick. A fixed bearing doesn't use slotted holes, it just uses a standard hole to keep it in place. It was funny. I went on the New River Gorge bridge tour when I was in undergrad. I know some of the ASCE folks did that here recently, and we were on the catwalk looking down. You could see the supports to the arch, and our structural analysis professor was there, and this one student went over to the professor and said, "I don't see a triangle and a circle down there. You lied to me." So, figured you all would get a kick out of that. Okay. Now, a fixed support resists motion, and I say all three directions, quote unquote, which basically means it resists force in the x direction, the y direction, but it also resists bending moments. So, at a given, let's say, roller support, we have a single concentrated load in the direction of that roller. That's the reaction, let's say F sub y or F or what have you. For a, for a fixed support, we have three unknown components: a force in the x direction, a force in the y direction, and an unknown concentrated moment right there at the support. Because a fixed support, it is meant to resist not only forces, but moments as well. Make sense? Okay. So what we're going to do is draw the shear and moment diagram for this structure. And you might have done this, you might not have. I'm not sure as some professors in statics cover it extensively, some cover it very lightly, and some don't cover it at all. So regardless if you've seen it or not, I think this will be a pretty straightforward problem. All right, sound good? All right. Now, I'm lazy, so let's see. There it is. What are we on? Example 18. Excuse me. Ooh, that is a little large. I'm actually going to stretch it out a little bit. Actually, let me move that. Let's move that over here. Okay. So, all right, we've got a couple concentrated loads. We've got a 2,000-pound load, and we've got a 4,000-pound load. The 2,000's mid-span between B and C, and this 4,000 pounds is on this cantilevered end. Now, I've got this distributed load. When possible, I like to take distributed loads and collapse them into a single point load. Now, I've got 400 pounds per foot acting over a distance of what? 4, 6, 16? So what's 400 times 16? That's where a calculator comes in. 6,400. Now, this load, think of it like it's a rectangle. And where's the centroid of a rectangle? It's right in the middle. So this rectangle is what? 16 feet long, so 8 foot from the left end. That's where that load's going to be, right? So I can collapse that into a single load of, let's say, $6,400. And what's that dimension going to be? 4 feet. Right? Because from the far left, it's 8. Does that make sense? All right, any questions? All right. What I'm then going to do is I'm going to say, all right, we need to determine these support reactions. Now, let's start to identify those. Now, these are hinges and rollers, so they both have vertical reactions, okay? So right off the bat, I've got to make a guess as to their direction. I'm going to take a wild guess and assume that they both act upwards. So we'll call this BY. We'll call this CY. Okay? Now, I'm guessing that they are upwards. If I do all of my math, write all of my equations of equilibrium, and I get a negative answer, it does not mean I need to develop significant emotional distress. It just means that I guessed the wrong direction. There's nothing wrong with that. Okay? Sound good? Now, I forgot one. This hinge technically has a reaction in the x direction, right? But what is that value going to be? 0. There's no loads in the x direction. So because there's no loads in the x direction, for now, I'm just going to ignore it. All right, sound good? Now, I've got I have 2 remaining equations of equilibrium because I've already used the sum of forces in the x direction with that horizontal reaction. I just sort of did that. If we want, we can be, methodical and just say, we can just say sum of forces in the x direction equals 0, and that means that bx equals 0. So if you want to say you've exhausted all of them. So we've got sum of forces in the x direction, we've got sum of forces in the y direction, sum of moments. Now if we sum forces in the y direction, we're going to have 2 unknowns, right? We're going to have by and cy. So that means we need to sum moments. And when you sum moments, it behooves you to try and eliminate one of the unknowns by summing moments along the path of one of those forces. So why don't I sum moments at, let's say, B? If I sum moments at B, I get no moment contribution from that by reaction, and I can solve directly for C. Make sense? Okay. So let's sum moments at B, and let's see what we get. So you just go through your forces one by one and start listing them out. So I'm at B. Let's just go through them one by one. Do I need to consider BY? No, it's going right through B, so it's a moment arm of 0. What about this 6,400 pounds? Do I need to consider that? Yep. Yeah. Okay. What side of the table should I put it on? Should I put it on the left side or the right side? The left side, because here's B, here's the 6,400 pounds, rotating like this, right? So it belongs on the left side. Now from B, how far is that force? 4 foot, right? So 6,400. Four foot. All right. What's next? We've got 2,000 pounds. Which side of the table does that go on? Same side. Moment arm of 6 feet. Remember, from B. Okay. Now, what's next? Well, we've got CY. CY, which side of the table do I put that on? Right side, because here's B, here's CY acting like this, so it's rotating like that. So CY is acting at a moment arm of, how far is CY from that support? 12 foot. Last one. We've got 4,000 pounds. Which side of the table does it go on? No, that goes on the left, right? Right. Moment arm, 15. Everybody okay with that? Any questions? All right. Now over here on the right, I'm saying everything on the left side's got to equal everything on the right. On the right, it's just CY times 12 feet. Okay. On the left, I just multiply and add. So 6,400 times 4 what is that? You know, just start at, you can do it all at once or however you want to do it. So what do we got? On the first one, we've got 25,600. Ooh, I can do better than that. All right. We've got 12,000. And we've got 60,000. So what do we got? What? 97,600. Did anybody else get that? You get that? All right. Yeah, because this one comes out to be 25,600, 12,000, and 60,000. So 97,600. What are the units? Foot pounds. We're multiplying pounds times feet. These are moments, so it comes out in foot pounds. So how do I solve for CY? Now, if I divide that, I get a number of, what is that, 8133.33? Now, did that come out, when we did all our math, did that come out positive or negative? Positive number, right? So that means that this is 81.30 or 8133.33 pounds acting upwards. In other words, we guessed that it acted upwards, and we got the right answer. I mean, if we guessed downward, we would have gotten the same number, but the math would have worked out. We'd got a negative answer. Make sense? Okay. What's left? Actually, let me do BY. So this is 8133.33. And how do we solve for that? There we go. I'm going to erase this because we're going to need some space here in a second. Okay. So to sum forces in the y direction, we just need to start tallying stuff up. So what do I have going down? I got 6,400, 2,000, 4,000, right? Make sense? What do I have going up? Well, I've got BY, and I got CY, but I solved for that. Sound good? Any questions? All right. So BY plus 8133. All right. That equals what? Yep. And what do we get here? What's that? We got it. It's up, yeah. But the number we get is what? 0.67 pounds. Make sense? So, excuse me. All right, any questions? Everybody good? Okay. Now, before I start drawing these shear and moment diagrams, I'm going to do something here to my screen. The first thing I'm going to do, I'm getting rid of that, okay? And I'm getting rid of that is, the reason I'm doing that is because that's fictitious. I made that up. I made that up to make my life easier when I was summing moments. That doesn't exist, okay? And I don't want that there to confuse what I am about to do. All right? So far, so good? Okay. Now, here's how this is going to work, okay? And if you need to create some room on your paper, you might as well go ahead and get ready for this now. I'm going to draw a bunch of vertical lines going down like this, okay? We'll draw a bunch of lines going down like this, and I'm going to have a shear diagram and a moment diagram. So you might want to make some room on your paper. So. Okay. That should be enough. So let me move that. Come on. There we go. All right. Now, the first thing that we're going to do is draw the shear diagram. Okay? So I'm going to strike a dark line. And I'm going to say that this line is going to be the shear diagram. Now, instead of putting units all over the place, I'm going to recognize that this is all going to be in pounds. All right. Sound good? Okay, now. So I want everybody to sort of pay attention to what I'm doing here so that everybody's aware of what's going on. Okay. When we draw a shear diagram, we literally just do what the beam tells us to do. And what do I mean by that? I start off at the very left end of the beam, okay? And I move from left to right, and I just look at the beam. So let's start off. If I start here and start moving across, the first thing I see is this uniformly distributed load, right? Now, it's 400 pounds per foot, okay? Now, let me ask you this. From here to here, that's 4 feet. So 400 pounds per foot times 4 feet is what? 1,600 pounds. Okay. So from here to here, I change 1,600 pounds. And I propose that that changes downward since the load is literally pointing downward. Make sense? So I propose that from here to here, if this is 0, this is, what was that? Maybe put right here. Minus, actually, no, let me raise that up a little bit. Say, minus 1,600. Sound good? Now, to draw the shear diagram in this range, the load, the magnitude of the load is constant, right? It's a constant 400 pounds per foot. So I propose the slope is constant. And what type of graph has a constant slope? A line, right? That's what a line is. That is the definition of it. So, that's a line. Does that make sense? Okay. So I'm moving from left to right, and I get to right here, and the beam goes, whoa, jump up some, right? Because I'm at negative 1,600, and the beam is telling me to jump up. It's telling me to jump up an amount of 4,266.67 pounds. Everybody see that? So if I'm at negative 1,600 and I go up 4,266.67, what does that put me at? There we go. So that puts me about, maybe about right there. 2666.67. Does that make sense? Okay, now, what's going on from here to here? All right, I've still got that distributed load. Now let's look at magnitudes. I've got 400 pounds per foot over a distance of 6 feet. So how much load is that? 2,400. So if I'm at 2666.67 and I go down 2,400, what's that put me at? There we go, 200. And what's that graph going to look like between those two regions? Linear. This is where a straight edge comes in handy if you all have, straight edge with you. All right, sound good? Then what happens here? Beam goes, whoa, you need to drop down right now. Okay, so I'm at 266.67. It tells me to go down 2,000. So if I'm at 266.67 and I go down 2,000, what's that put me at? There you go. 0.33. Yep. So probably somewhere about right there. Say. Put that right here. Does that make sense? Any questions? All right. Now we keep going. All right, what do we do from here? From here to here. We got another drop, right? So if I'm at 1733, negative 1733, and I drop, how much am I dropping? 2,400, because it's 400 pounds per foot over a distance of 6 feet. So if I'm at 1733, negative 1733, and I drop 2,400, what's that put me at? There we go. So all the way down here. About like that, right? Now what do I do? I got a crazy jump, right? So if I'm at negative 4133 and I jump up 8133, what's that put me at? 4,000 even. I got a crazy jump. Now, what's going on from C to D? What's the beam telling me to do? Nothing. There's no change. So if the shear is 4,000 here, it's 4,000 here. It's 4,000 here. It's 4,000 here. So now what's the beam telling me to do? And if I'm at 4,000 and I go down 4,000, what's that put me at? Ladies and gentlemen, there's your shear diagram. Not too bad, right? Pretty straightforward. Anybody have any questions?
So this, if this bridge works, then this should always be 0.
Okay. No. All right. Let me say a couple things about that. Drawn properly, a shear diagram and a moment diagram will start and end at 0. Now, if you have, let's say, a fixed support, you might immediately drop down some or raise up some or what have you. But one way or another, you should start and end at 0. The reason why is because sum of forces equals 0. It has nothing. Now, the point you had mentioned, you said, does that have to do with shear stresses? No, that's completely different. We're still looking at moments and forces. We haven't gotten into stresses yet. To determine whether or not this bridge is safe or unsafe, what we would then have to do is we'd say, all right, here's the shear force. What is the shear stress? And does that exceed limits or what have you? Make sense? All right. Any more questions? This is good stuff. Okay. Now, to draw the moment diagram, we must integrate that. But I don't like calculus if I can avoid it. Would you all like to do the integration? I can see you all just, you never reach your limit when it comes to calculus, right? I got the jokes. All right. In all seriousness, though, integration is little more than computing the area under the curve. So I propose that we integrate this by just computing the areas. Let's start off with a simple one. What is the area right here, from here to here? What is that area? Well, how tall is it? It's 4,000 tall, and it's 3 wide. So this is positive 12,000. Is that fair? Okay. Let's start off with another simple one. What about this one? How do we calculate the area right here? 1/2 base times height. What is the width? It is... No, I'm talking about from here to here. 4. And this is 1,600, or negative 1,600. So what is 1/2 of 1,600 times 4? There we go. So this is I can do better now. Hold on. Bless you. All right, everybody good? Now, what about these regions? Well, you can do this one of two ways. You can either say it's a rectangle and a triangle, or do y'all remember how to compute the area of a trapezoid? You just take, if you've got this region, just take the average of that and that, multiply it by the width. Y'all remember that? Well, we can try it out. What's the average of these two numbers? Add these two numbers, divide them by 2. Say it again. 2933.33. And then if I take that and multiply it by the width, 6, what do you get? So basically, I propose that entire area is negative 17,600. And if you want, cut it up into a rectangle and a triangle. All right? If you want, you can go ahead and do that. The question, though, is, if you do something like that, how tall is the rectangle? It's 1733, right? How tall is the triangle? Which is 2,400. How did I do that? 400 pounds per foot over 6 feet. That's how much we changed. Does that make sense? So, you can do it either way. Let's take this one up here. Somebody tell me the area of this segment. Remember, just average them, multiply by the length. Because you're sort of just splitting the difference and saying, we'll take this a little bit, flip it right there. That's, okay, so what, 8,800. Anybody else getting that? Okay. Okay. Now, I want to do a little bit of a check right now. we're integrating the shear diagram, which basically means we're computing moments. All right? Do me a favor. Add up all the positive numbers and tell me what you get. Huh? Well, we got this and this. The positive areas, I mean. Say it again? 20,800. Now add up the negative numbers. 20,800. In other words, when we draw our moment diagram, we're going to start at 0 and we're going to end at 0. Why? Because the positive areas equal the negative areas. Now, that will not always happen. And there's a very clear case where it won't, and that's cantilevered beams. And we'll see that here in a little bit. Everybody good so far? Now, to draw the moment diagram, the first thing I'm going to do is I'm just going to worry about the magnitudes. Okay? So, first off, when I draw the moment diagram, I don't really care as much about the loads. I care about it a little bit, but not substantially. Now, the moment's going to be in foot-pounds, right? Pounds times feet. All right. Now, let's look at what this is going to look like. Okay? I'm going to start off at 0. Now, without drawing anything, let's just look at our magnitudes. Now, if I start at 0 and I go down some, I'm looking at the areas. I go down 3,200. That puts me down right here, right? 3,200. I'm not drawing anything. I'm just doing the magnitudes. So maybe something about right here. Now, if I'm at 3,200 and I then go up some, I go up what, 8,800? What's that put me at? 5,600, so maybe somewhere right here. Now, if I'm at 5,600 and I go down 17,600, what's that put me at? Negative 12,000. So maybe I got to drop that down somewhere about right here. If I'm at negative 12,000, I go up 12,000, what's that put me at? 0. Now, is everybody okay with that? Okay. Now I want everybody to pay attention what I'm going to do right here. Okay. The magnitude of the shear is equal to the slope of the moment diagram. Now a simple way that you can do this is, let's look at this first region. Okay. Now I want you to look at the magnitudes. Would you agree that the shear magnitudes go a little to a lot? Everybody see that? A little to a lot. Now, let's think about that. What does very small slopes look like? Maybe something about like that. What does a very large slope like? Maybe something like that. Make sense? So, little to a lot, little slope to a lot of slope, I propose that it looks something about like this. Maybe drop that down a little bit. All right. You see how I did that? A little to a lot. Sound good? Now the next region. Backwards. Because we're going from a lot to a little. So I propose we go a lot to a little. Sound good? I propose our moment diagram in this region looks like that. That makes sense? Okay. Now, so tell me, what's it look like here? Does it do that? Yeah, so does it do this? No, it does that, right? Let's see. Something about like that, right? About right there. Now, what about right here? Okay, constant shear. Okay, so it's a constant slope. Now the area is positive, right? So it's a positive slope. What does a line with a positive slope look like? It looks like this. Not like that. That's negative slope, right? So it looks like this. So straight line. And there you go. So, from a design standpoint, let's look at it like this. In most cases, when we design for shears and moments, we really care mostly about magnitude. So what is the largest magnitude moment on this beam? Magnitude. 12,000. So I would design this beam for a bending moment of 12,000 foot-pounds and a design shear of, what's that? No, those are, the areas are the moments. I'm talking about the values, the 4133, right? The maximum shear that this thing is seeing is negative, or the magnitude is negative, and it's 4133. Does that make sense? So as the design engineer, you would size this beam to resist a shear of 4133 pounds and a moment of 12,000 foot-pounds. Does that make sense? Anybody have any questions about that? Everybody good? Okay, this is good stuff. All right. Let's see. Everybody good? Yeah. Wait, where? 20, you mean like right here to here? Okay, all right. That came from looking up here at this load diagram. So I'm looking from like right here to right here. Okay, so this is the load that changes, right? Okay, so this is 400 pounds per foot, and it's over a distance of 6 feet. So between here and here, that's a total change of 2,400 pounds. Make sense? So if I'm at, let's say, 2666.67, and I go down 2,400, what's that minus 2,400? It's 266. Does that make sense? Is that clear to everybody else? I want to make sure this stuff is clear. This is one of the most fundamental analysis tasks that an engineer does. So, you good? All right. What about everybody else? Let's see what time it is. Oh, we got plenty of time. Sound good? Okay. All right. Okay. Now, this one's going to be a little different, okay? The loads are easier, but we're going to find some things that might bug us a little bit when we do our analysis. For instance, when we draw the shear diagram, we're going to have a different result than we did last time. Remember how we computed all the areas? We got the areas equaled 0. You know, the area up top equals the area below. That's not going to be the case here, okay? They're going to be imbalanced. And there's a specific reason why they're going to be imbalanced, but we'll see that as we go. Okay. Any questions? All right. So we got a cantilevered beam. We have a 1,000-pound load right near the support, but we also got this distributed load out at the end. So we're going to handle this Very similar to what we did last time, but we got to handle that fixed support a little differently. All right. And again, I'm lazy. My goodness, that is a large beam. Although I am going to stretch it out a little bit. Makes drawing the shear and moment diagrams a little easier. All right. So the first thing we need to do is we need to handle that support. How many reactions are we going to have at that support? Well, 2 for this beam, but how many theoretically would we have? 3, right? Because if it's a fixed support, it has an X reaction, a Y reaction, and a moment. Okay? Now, what is the X reaction going to be? 0, right? So if we want to exhaust those equations of equilibrium, we can say sum of forces in the X direction indicates that AX is 0. But we're going to have a vertical reaction and a moment reaction. Let's start off with the vertical reaction. We have to assume a direction. What direction do you want to assume? Up. So let's put, I don't know. How about that? Sound good? Moment reaction. Do you want to assume clockwise or counterclockwise? Clockwise. Okay, we'll assume clockwise. All right, sound good? And again, those are assumptions. If we do our math and we get negative answers, no need to develop significant emotional problems, just means we guessed the wrong direction. Sound good? Now, I don't like distributed loads when I'm determining reactions, so I got 100 pounds per foot over a distance of 15 feet, so what should I do with that? There you go. So does that make sense? Now, luckily all our reactions are in the same spot, so it doesn't matter if we sum forces or sum moments. What do y'all want to do? Let's do moments. Okay, we'll do moments. So we'll sum moments at A, let's say. All right. So what do we got going on? Well, I'm at A. Does AY cause any moment? No. Now I do have MA. I have a concentrated moment there, so I have to include that. And I've got that drawn over here. Make sense? All right. What else do we have? We've got 1,000 pounds. What side of the table does that belong on from A? Left side. And it's at a moment arm of 5 feet. All right. What's the next one? We've got 1,500 pounds. What side of the table does that belong on? Bless you. Left side. Now, how far how far is that from A? Say it again. There you go. Anything going on the right side? No, we got everything, right? So over here, this is 0. So I'm going to have MA plus what? So, well, I got what was that, 38,750? So MA plus 38,750 foot-pounds equals 0. So what's the solution to that equation? Negative 38,750. So MA is negative. Now, again, when you get a negative support reaction, it does not mean you need to develop significant emotional problems. It just means that we guessed wrong. We guessed clockwise. Wrong. It's counterclockwise. So this is 38,750. Counterclockwise. And if you want, you can say, all right, let's go up here. Let's erase that and put that like that. Do that like so. Sound good? Any questions? All right. AY. I'm curious. Can anybody just look at this and tell me what AY is going to be? Isn't that what I have? Oh, my LB, it looks like a K. No, I wrote LB, but I've got this sort of like, it's like a fat font there. So it is LB. But yeah, you know, I was kind of self-conscious about my handwriting, and then, you know, you just had to. I see how it is. Okay. No, it's fine. No, it is foot-pounds, so. I got to have fun with it. All right, so let's just follow the, I mean, we can draw the table if you would like, but how much do I have going down? Somebody other than you. How much do I have going down? Well, no, well, think about it like this. All right, I've got 1,000 pounds going down, and I got 1,500. So what's my total amount going down? 2,500. What's the only thing going up? So AY is 2,500 going up. Does everybody see that? Okay. I mean, you can go through and draw the table if you'd like, but I'm just going to shortcut it. Hold on, wait. Let me draw that as a separate L and a separate B. Nope, didn't work. Since somebody had to make comments about my handwriting. All right. All right, sound good? Okay. All right, now we're going to do the same drill as we did last time, and we'll draw a bunch of vertical lines at each of these given points and handle it the same way. All right, so. All right, that's probably good for right now. First thing, shear diagram. How are we doing on time? Doing good. Okay. So, like before, I do what the beam tells me to do. So I start at the very beginning at 0. Now, at the very beginning, I got two things going on. I have a shear and a moment. I'm drawing the shear diagram. I don't care about the moment right now. We'll deal with that later. All right, sound good? Okay, right now I have a force of 2,500 pounds telling me to go which direction? Up. So if I'm at 0, very first thing that I do, I go up to 2,500. Actually, I'm going to keep up with my color scheme that I used last time. Now, what do I do from A to B? Nothing. Straight line, right? Just horizontal. Because between A and B, how much load is being placed? Nothing. So we got that. Now what do I do? Bam, go down 1,000. So that puts me where? All right. Now what do I do between B and C? Not a thing, right? Straight line, no change. Now, I didn't do this before, but I'll go ahead and do it now. Remember, that 1,500 pounds, that dashed load that you have at the very top, I made that up. It doesn't exist. What do I do from here to here? Linearly go down. Now, 100 pounds per foot for 15 feet, that's what, 1,500 pounds? So if I'm at 1,500 and I go down 1,500, that brings me down to 0. So the equilibrium gods are happy because everything going up equals everything going down. Sound good? All right. Now, just like last time, compute areas. All right? So let's handle this like that, like that. What's the area of this first rectangle? Right here. 5 times, yeah, 2,500, which is, and that's positive, right? What about right here? What about here? There we go. Now, everybody good? I want to remind you of something. Okay? Let's go back to our previous example. This was our shear diagram from the previous example. And remember, all the positive areas and all the negative areas canceled each other out, right? We got a problem here with this one because there are no negative areas, right? They don't exist. But how much positive area is there? $38,750. Does that number seem somewhat familiar? That's the moment reaction. Now, I've got too much positive area. So in order for everything to balance out to 0, I propose that when we start our moment diagram, we start off by drawing down. Because think about what's going to happen. All right, so here's our moment diagram. All right. We start off at 0. Now, we start here. What's the first thing that we see in terms of moments? 38,750. Now, I want you to do this mentally. Okay, now there's 2 ways theoretically we could handle this. We could take that and draw it up, or we could draw it down. If we drew it up, all these areas would increase, right? We would never come back to 0. So I propose we start off down here. Why? Because as we draw the shear, or as we draw the moment diagram, we're going to see how this all comes back to 0 here in a second. Sound good? All right. So if I'm at negative 38,750 and I go up some, I go up 12,500, what's that put me at? $26,250. That make sense? What? Is it 750? Oh, whoops. Wait, no, there's a 500 in there. Is that? Yeah. That's negative. Everybody else got that? Did you get that? Okay. All right. Let's just go ahead and do the rest of them. If I'm at 26,250, negative 26,250, and I go up 15 grand, what's that put me at? And then if I'm at here and I go up, that's going to bring me back to 0, right? So obviously, this moment had to start off negative. It couldn't start off positive. Make sense? All right. Now, what do the segments look like, okay? From here to here, what's it look like? If I were to draw it in. What's the value of the shear? It's constant. Constant shear, constant slope. What about from here to here? Okay, so let's go ahead and fill those in. So something about like that. Something about like that. I promise that's supposed to be a straight line. I mean, we got folks in here making fun of my handwriting. I'm kidding. I've actually tried to use it on this thing, and it gets wonky. So, all right. The last one is this triangular region. Now follow along with me. Lot to a little. Slope is lot to a little. So. Something about like that. It's probably a good idea on your homework and on our second exam. Remember, we don't have exam, we have celebrations. But on your second exam to bring a straight edge for stuff like this. Any questions? Okay. That's basically everything on homework 4. I really, at least very briefly for the next couple minutes, just want to at least introduce what's coming next. Okay. What's coming next is the idea of stresses and beams. And we're going to look at, you know, a multitude of different types of stresses and different types of beams. We're going to look at normal stresses, shear stresses. We're going to look at composite beams, non-symmetric beams. We're going to do a lot with beams. They are the most fundamental element in engineering, one of the most fundamental elements. I mean, you've got beams, you've got pipes, you've got, pipes carrying fluids, beam carrying stresses. They're one of the most fundamental elements. That and maybe a circuit. I think that's about as fundamental as it gets. Just about any mechanical or civil engineering system that's being subjected to forces contains elements that are being bent in one way or another. Just no way around it. So stresses and beams are very fundamental. Okay. In order to assess them, we need to understand two concepts: shears and moments, which we just talked about, and we need to understand section properties. Now, if I take a beam subjected to any random loads and cut a section, I get at most 3 unknown components of forces, right? A force in the x direction, a force in the y direction, and a moment. right? Now, let's think about this. Sum of forces in the x direction would reveal some axial force P inside the beam, right? Now, we've already handled stresses like that. Remember, sigma equals P over A, the stress due to an axial load. We've done that, okay? So we don't have to cover that, or at least we should recognize it when it shows up, okay? Now, bending moments cause normal stresses, which we will try and figure out the formula, and shear forces generate shear stresses. Tau equals something. Now, we'll handle the shear stuff later. Right now, I'm going to concern myself about the bending moment. I don't want to get too heavy into this derivation. I do want to take my time with it. We are going to make some assumptions, linear behavior, small deflections, and strain compatibility. We will define very rigorously what that stuff means next time. But we go through and start to define the stresses on some arbitrary cross-section. And one of the ways that we do that is we reference a lot of our equations and information from the centroid, hence why we talked about all that centroid and moment of inertia stuff later. You go through the derivation, we are going to see a integral of y squared dA, and it's kind of funny how that's a moment of inertia. I'm not going to go through this in any significant detail now. We're going to talk about this next time. So, I want you all to sort of, right now, digest the beginning stuff, moments of inertia, shear and moment diagrams. You understand that? This stuff will come very well. That's all I got for you this time. We will take this derivation one step at a time on Thursday. I'll see you then. Hold on for 1 second.